Hi, and welcome to the Simulation Step-Up series. This episode is an introduction to nonlinear analysis in SOLIDWORKS Simulation. We'll look at the differences between a linear and a nonlinear systems, see what assumptions are made in linear systems, when do they break down, and when is it warrant to actually do a nonlinear analysis. We'll look at the different shades of nonlinearity in structural problems. And finally, we'll take a look at some general guidelines and flowcharts to help you make the decision regarding whether a linear analysis or a nonlinear analysis is the way to go. So let's get started.
A linear system is a proportional system, which means the response of a system such as displacements, deformation, etc., always remains linearly proportional to the applied loads. So this also assumes that the material is linear, deformations are so small that the final shape is almost the same as the original shape, and finally the applied loads are constant, meaning the magnitude, orientation, and the distribution does not change during the course of deformation. So, for example, if the load is multiplied 2x times, then the response, such as displacement, stresses, etc., will also be 2x times, and so on. However, much of the world behaves nonlinearly, which means the above assumptions may no longer hold true. And consequently, structural nonlinearities show up in the material behavior, such as plasticity effects, elastomeric effects, and so on. The geometric stiffening or softening of the structure as it deforms is another common nonlinearity. And finally, the boundary or contact, where the physical interaction between surfaces can alter the rate of load transfer between parts depending upon the loading area, is also a common type of nonlinearity as well. In simple words, a nonlinear system is one where the applied force and corresponding response in the structure is no longer proportional or linear as illustrated in this graph. However, a nonlinear solution or response can be evaluated as a series of smaller linear solutions. Like this illustration here, where the end-to-end length is not linear and needs to be measured, the path can be broken down into a series of linear distances and measured, sum them all up, and we have the desired length. So, do you think you need to consider nonlinearity? It really depends on the forces involved and the response of the system being analyzed. This presentation is geared towards helping you making that decision and understanding that while a linear system is a great place to start, a nonlinear system does provide more accurate and realistic results. Nonlinearity is a concern whenever the response at the operating load causes strain levels in the material beyond the portion of the stress strain curve that can be reasonably approximated as linear. Remember the degree of nonlinearity concept. Many materials have curves that can deviate in a small linear manner for large amounts of strain, and so a nonlinear solution may not be necessary. On the other hand, many curves deviate from a linear almost immediately to such a degree that only rough trend studies can be made with a linear approximation. The constant of proportionality is in a linear material model is called the Young's modulus. This represents the slope of the linear portion of the stress strain curve. For highly nonlinear materials, this modulus is only applicable at very low strains. Nonlinear behavior of common engineering materials are specified through their stress strain curves in SOLIDWORKS simulation. When the material has the same response in both tension and compression, it is said to be symmetric. SOLIDWORKS simulation allows you to input both symmetric as well as asymmetric stress strain curves. Cast iron is a good example of an asymmetric stress strain curve, as it is stronger in compression than in tension. Now, there are several types of material nonlinearity that might be present in a structural analysis, and these can be characterized by stress strain curves for that material. A nonlinear material can be modeled as a nonlinear elastic, where the part returns to zero strain state when the load is completely removed. Or it can be modeled as elastoplastic, where permanent strains accumulate once a material yield strength is reached. Additionally, an elastoplastic material can be defined as bilinear, where only the elastic modulus and the hardening modulus need to be entered in the software. You can also enter a multilinear stress strain curve, where true nonlinearity of the plastic range can be captured with a series of points. The other material models supported in SOLIDWORKS simulation include hyperelastic materials for elastomers and viscoelastic for time-dependent response such as creep. Finally, a nitinol model is available to simulate materials such as shape memory alloys as nitinol, typically used in medical stent applications. Keep in mind that these material models do require a detailed knowledge of the material behavior as they don't behave like any other common structural materials. Now, stress strain curves for metals are typically measured in tension or compression tests. Typically, a doggone specimen is used and certain load applied and the response of the strain measured. That gives one data point on the graph shown here between the stress and strain. Then multiple load cases are tested and the measured response used to obtain the stress strain data as illustrated in this graph. The tension tests for metals are the ASTM E8 and allows for multiple strain rates, multiple temperatures, etc. The graphs shown here show the stress strain curves for AISI 4340 steel and 2024 aluminum. You can clearly see that the scale curves show consistent slope of the Young's modulus until yield. The aluminum curves show variation in the stress strain response as different material orientations are examined. The curves also show that 2024 aluminum has an asymmetric response and its tensile and compressive response is completely different. Both these curves are taken from the MK Handbook 5H, which is a publicly available resource and has a lot of good material reference data. Now, these curves on this slide for Noril, a GE Plastics PPO, were measured using ASTM D638, which is a standard tensile test for plastics. The stress strain curve on the left shows how it can vary with injection molded flow directions. The curves on the right show how the same material can have different stress strain responses based on strain rates and loading rates as well as temperatures. Hopefully, you can see from these examples how the investigation of a nonlinear material can actually get very complex. The general recommendation is that you get your hands on the most applicable stress strain data for the materials that you're considering using to determine if the material nonlinearity is even an issue for the strain levels you're operating in. This level can be determined from an initial linear material analysis, and if you decide to use a nonlinear material model, try to find the stress strain data that best represents your environment, and if necessary, bracket the results with two or three different curves to see how sensitive the response of the structure is to this nonlinearity. And finally, it is always a good practice to back up your analysis with test data. Now, another class of common nonlinear materials that warrants discussion is hyperelastic materials like rubber, foam, etc. They are characterized by the capacity to take large amounts of strain with relatively small loads. Even though we treat the materials as elastic, isotropic, and incompressible, their behavior is very complex and depends on the loading mode. The amount of strain accumulation can be anywhere from 100% to a whopping 800% strain, which is literally 8x times its original size. Now, due to the complex behavior, the elastic constants or material constants are derived from the elastic strain energy density. These material constants is what is needed in SOLIDWORKS simulation. The good news is that if you're simulating these materials, then it is highly recommended to get the stress strain data from the material vendor and use them in SOLIDWORKS simulation. That way the program will calculate the material constants and use it for the solve rather than you trying to figure out how to calculate the material constants. Now, with hyperelastic materials, once a material is manufactured, it undergoes cyclic loading and unloading for at least about 25 to 50 times to stabilize its response, as shown here. Now, during the initial loading and unloading of these raw materials, notice how the stress strain response differs or is offset from its previous cycle of loading and unloading. After repetitive loading and unloading, the material starts to follow a constant loading and unloading path, and the stress strain data corresponding to this stable configuration is what is needed in the analysis input. Here's a quick illustration of the type of testing of these hyperelastic materials. Unlike metals, for hyperelastic materials, the tests are performed for uniaxial tension, biaxial tension, and planar or shear tension cases with different specimens. The stress strain data obtained from these tests is what SOLIDWORKS simulation requires. At the minimum, one of these test data is needed to run the nonlinear analysis for the material. If you can get all three test data and input in the program, it will only ensure more precise calculations of the material constants and also of the structural response. To illustrate the material nonlinearity, let's take a look at this pen assembly. We want to analyze the flange by pulling it on one end with a 0.25-pound load as shown. We want to release the load to see how the structure responds to a linear material and a nonlinear material model. The loading and unloading behavior can be easily accommodated in SOLIDWORKS Simulation nonlinear setup by associating the load with the time curve as shown. We all know that if we pull the flange just a little bit and then release, it's probably going to return to its original shape and size, having that elastic effect with a linear model. However, if we pull it way too much and then release the load, then we should see some sort of permanent deformation. We all know this, right, from experience. I have personally broken at least a dozen flanges. So on the left, we have a linear elastic model, and on the right, we have a nonlinear plasticity model. And for the plasticity model, we are assuming that the material is bilinear, meaning the plastic portion of the curve beyond the yield point is modeled using a single value called the tangent modulus or the tangent slope. So the material behaves pretty much linear in the plastic region, but has a softer response. Comparing the results clearly illustrates the vast differences in the shape, deformation, and overall response in the flange. The linear material overlooks the yield stress point and still uses the elastic modulus in the linear range to calculate the final stress and deformation. The nonlinear plasticity model predicts the correct response since it tracks when the material yields and what happens beyond that point in the plastic region. So when the load is completely removed, it accumulates permanent strains and stress in the flange, causing it to have a permanent deformed shape as illustrated in this video and also the graph below that video. To sum up the discussion on material nonlinearity, note that there can be significant differences between the results from a linear versus a nonlinear model. The higher the strain levels, more nonlinearity can be expected. For everything made out of steel, nonlinear modeling is pretty straightforward. However, for other materials, it is always recommended to get a copy of the stress strain curve and review to get a feel for the nonlinearity. A linear model can be still good enough for trend studies in a moderately nonlinear situation such as low strains, as the nonlinear response more or less would be similar to a linear response. Many components tend not to operate with stress or strain levels near the yield point. There is no need to model that plastic response, as yielding is an unacceptable performance point. Also remember that fatigue strengths for most materials are well below the yield. So if material nonlinearity and a cyclic loading is a concern, you may be better off trying to optimize a problem until it's linear. So one final note on this, and this goes towards correlation and prediction of analysis results to test data. A linear analysis can only predict the onset of yielding. Once a reasonable portion of the linear model begins to yield, the loads all redistribute and it becomes a different problem. Attempting to correlate the final prototype that is loaded to failure to that of a linear analysis will not make any sense. Geometric nonlinearity becomes a concern when the parts deform so much that the initial model assumptions are no longer valid. These typically arise from the effect of large displacements or large rotations. The majority of geometric nonlinearity work uses get into involves stress stiffening. As mentioned earlier, the best example of stress stiffening is the pitch change on a guitar string as it is tightened. The Young's modulus of the guitar string does not change, but the stiffness of the string changes nevertheless. Now, flat plates under out-of-plane loading with all pin sides are also common nonlinear geometric stress stiffening cases. In the paper traced shown, as the distributed load on the face of the plate is increased, a linear model will actually show a proportional response, but a nonlinear model will show the displacements tapering off as the load increases due to the stress stiffening effect. We'll explore this test phenomenon in the next few slides using a test model. Now, other common stress stiffening examples include snap-through or buckling problems, often referred to as bistable or multi-stable systems. Many snap-through problems behave linearly until a small amount of force suddenly causes a large deflection, and as the loading decreases, the displacements in the system still increase until a secondary stable configuration is reached. SOLIDWORKS simulation can predict this complex physics using an appropriate numerical control technique called the arc length method, which works on both parts and assemblies. Lastly, another type of nonlinearity that warrants introduction in this section is the last strain scenario. This is always coupled with a nonlinear material model as it involves large plastic deformation of parts. Coal heading, rubber seal compressions, and metal forming are some good examples of last strain responses. Geometric nonlinear, Geometric nonlinearity is also labeled as large displacement problem and is caused by tensile stress which results from larger displacements. The actual displacement in the model is not an indication of nonlinearity, nor is the tensile stress magnitude. The in-plane effects accounts for the stiffness of the structure and is actually a function of loads as well as deflections, which themselves are functions of load. Now, in this example, let's go ahead and examine a flat plate which is pinned on all four edges. A shell mesh model is used and a uniform surface pressure is applied on this plate. The pressure magnitude is actually controlled by a variable in a design study from 1 psi to 10 psi. Now, if you're not familiar with design studies, you can read about them in the online help or review the Simulation Step Up series episode chapter, chapter number 303. Now, let's review some of the results between running this problem as a small displacement versus a large displacement, as well as turning the in-plane effects on. The plots actually show the displacement response at the center of the plate for the linear solution as well as some of the other stress stiffening nonlinear options. As the pressure is incremented from 1 psi to 10 psi, the linear solution that assumes small displacements and no stress stiffening effects shows a typically linear response as shown on this graph. Now, with the in-plane effect turned on, the response is more or less the same as the linear solution. With the large displacement flag set prior to the run, you can see in the bottom left plot the response is definitely nonlinear in nature. Now the question remains as to how nonlinear it is. Here is a stress and displacement comparison for both small and large displacement conditions. Now, plotting this response side by side, you can see the nonlinearity for both stress and displacement is nearly 78% even at 1 psi loading and becomes almost 95% different at 10 psi load. In a more complex example, this flat wall tank is subject to a pressure loading that increases in depth, as would be the case of, let's say, this tank is filled with water or some other liquid. The setup for this model is shown. A quarter symmetry model is actually used and the problem is solved using small displacements as well as large displacement options. The results clearly show a huge difference between the displacements and stresses for both scenarios. Note that the predicted deformation of final shape is vastly different as well. So the question is, which is correct? When the difference is significant, as is in this particular case, the large displacement case should be considered more accurate as it accounts for the correct nonlinear behavior. To sum up, you saw how this particular study that we reviewed confirms that it is nearly impossible to estimate the degree of nonlinearity in a stress stiffening situation simply by evaluating displacements. SOLIDWORKS simulation evaluates the effect of large displacement by comparing the model displacements with an internally calculated characteristic length. It automatically displays a warning message if the max displacement exceeds this internal flag. But what good is it if it does not always point out stress stiffening? Well, it's better than nothing. Now, to truly determine if large displacement effects come into play is by comparing the small displacement and the large displacement results. So you can use simplified models to determine the significance, and using in-plane effects for static studies may not yield the expected results. So always use large displacement if in doubt. And finally, if small displacement and large displacement results differ only in magnitude, trends using small displacement results will still be valid. The last type of nonlinearity that we will review in this presentation is the boundary nonlinearity. Now, boundary nonlinearity stems from load-dependent variation in boundary conditions or loads and restraints. If the orientation, distribution, or magnitude of the applied load or the load path changes as loading is increased, a nonlinear model might be required. The most common type of boundary nonlinearity are the contact problems such as pounding of structures, fitting problems, gear tooth contact types, and assembly operations. Now, contact conditions model the physical interactions between the boundary of two or more parts. In many cases, the standard load or restraint will actually fail to provide the realistic response and may even introduce some sort of artificial stiffness into the system that can cause unreal system responses. Here is an example of contact nonlinearity on a gasket assembly operation. The nonlinear analysis is actually solved as a 2D axisymmetric problem. This is a great place to mention that if you end up doing a nonlinear analysis, see if there is any way to analyze a portion of the geometry or use symmetry options or even to solve the problem as a two-dimensional problem. This would help solve the solution much faster, but also help in getting that granularity in the mesh that you want, which otherwise you might hesitate to do so on a full 3D model. Notice that in the video how the top and bottom plates squeeze the sandwich elastomer first and then a side clamp is pushed, creating further deformation. You can clearly see how the contact pressure or the stress and the contact areas are constantly changing as the squeeze force increases. This cannot be captured by a linear system or by making any assumptions on loads and fixtures. Bottom line is contact nonlinearity is the right way to solve these type of problems. In summary, contact conditions are very easy to account for in SOLIDWORKS Simulation. Now you can review the Simulation Step-Up Series episode chapter number 104 titled Modeling Contact in SOLIDWORKS Simulation to learn in detail about how to use contacts in SOLIDWORKS Simulation. So all of the nonlinearities that has been discussed can be addressed in SOLIDWORKS Simulation. As you move from basic to the advanced simulation packages, you're provided with more and more options or tools to accurately capture the nonlinear behavior. Let's start with SOLIDWORKS Premium. Contact analysis, or the capture of multi-geometry interaction, is a nonlinear effect falling into the boundary nonlinear category. Friction can also be included in the contact definition at the linear static analysis level. Now, there are also tools to include geometric nonlinearity, which is available by choosing the large displacement option as shown. Choosing the in-plane effect also turns on a nonlinear effect on the solution. If the in-plane effects are considered in the analysis, the stiffness of the structure will be a function of loads as well as deflections, which themselves are functions of loads. So using this in conjunction with the large displacement option will probably make more sense to calculate the contributions of the in-plane effect to the overall geometric stiffness. But keep in mind that as a user, we have no control on how the nonlinear solution progresses and completes in a linear static situation like this. Now, as we move into SOLIDWORKS Simulation Professional, in addition to the options discussed previously, you have the option to include the in-plane effects of stress stiffening slash softening behavior in frequency analysis. A good example would again be a guitar string where the stiffening or tensioning of the wire increases the frequency or pitch and loosening the string has the opposite effect. Also included in Simulation Professional is the drop test analysis, which combines nonlinear and transient dynamic effects to calculate the response of a structure. And finally, in SOLIDWORKS Simulation Premium, there are two additional tools available. One is providing full control over the nonlinear solver, and secondly, allowing to simulate exact material responses using various material models. A nonlinear material model allows to input stress strain data for metals, plastics, elastomers, nitinol, and so on. To fully understand the benefits of nonlinear control, it is important to know that that with all of the nonlinear modeling capability in SOLIDWORKS Premium and SOLIDWORKS Simulation Professional, only the final results are available. This may suffice for a system where the final response can be used to make a decision assuming the load is applied proportionally. But in scenarios that involve a non-proportional path for loading and for a nonlinear and also by using a nonlinear material, a full nonlinear solution is required to properly understand the system response from zero to the fully applied load, as the interim results may be needed to make the design decision. And finally, let's wrap it up with looking at some guidelines as to how we can actually determine if the problem can be solved as a linear problem or a nonlinear problem. Now that you have learned about the different types of nonlinearity, let's go ahead and review some simple guidelines. So always start off with a simple linear study to make sure you understand all the interactions and potential nonlinearities. Nonlinear solutions can take 2 to 10 times longer than a linear solution on the same mesh. So it is definitely worth validating loads and restraints faster with a linear model first. If the linear and nonlinear results are different, then go with the nonlinear results as they will be more accurate. Now, additional time and resources may be required to complete a nonlinear analysis. So the question is, do you need extra training to run nonlinear problems in SOLIDWORKS simulation? For large displacement, checking the large displacement flag in the study properties does not require any additional knowledge of FEA or SOLIDWORKS simulation in a standard static study. For contact analysis, as interactions become more complex, some training knowledge will be helpful to understand the proper selection of source and target contact geometry, plus which contact formulation works best for a particular problem. Now, when it comes to material nonlinearity, it is the most complex of all the nonlinearity that we have discussed so far. In addition to understanding the differences in the various material models, a design engineer should also get some exposure training to material mechanics involved in the problem. There are a number of books, web resources, and testing labs that offer courses that can help you understand the nonlinear material effects. The next few slides illustrate a flowchart that can be used to easily capture and evaluate the case for nonlinearity in your design validation process. You can actually start by answering some simple or basic questions as shown here. So for example, do you have the material property information? Are the stresses close to or above the yield stress? Are there large displacements involved? Are there contacts involved? So depending upon how you answer the questions, you can actually start off with a linear static analysis or proceed to evaluate the case for a nonlinear analysis. Now, once you decide that nonlinear is the way to go, then the next step is to understand the geometric nonlinearity aspect in your design. This flowchart is meant to guide you through that decision-making process. Next, we have a visual aid via this flowchart to understand and establish if boundary nonlinearity needs to be considered in your simulation process. And finally, the most complex nonlinearity, which is the material nonlinearity. Here is again a nice visual aid to establish and understand the material you're using and how you might want to consider using a specific material model for the analysis. Now keep in mind that these flowcharts are available as a reference only and an attempt to help you making that right decision on nonlinearity. It is in no way meant to replace any training that you would definitely need while dealing with nonlinear analysis in SOLIDWORKS simulation. This concludes our introduction to the various types of nonlinearity in SOLIDWORKS simulation. We discussed the primary types of nonlinearities in structural analysis and how they may be accessed in various packages. We spent a good deal of time reviewing some examples of stress shifting, since this is the most common and difficult nonlinearity to predict. Simply looking at the displacement magnitude is not sufficient, nor is waiting until the large displacement warning pops up. In general, for thin wall systems undergoing displacements in the order of magnitude of the wall thickness itself, stress shifting effects should be considered. And finally, we did review some guidelines and flowcharts to understand how to incorporate nonlinear analysis in your day-to-day design work. You can always contact your local SOLIDWORKS reseller for more in-depth training or support on nonlinear analysis using SOLIDWORKS Simulation in your design work. Or you can always review the online help for a more detailed description of the features discussed in this presentation.
That concludes this presentation. To review this presentation and several other episodes on the Simulation Step-Up series, please visit the Simulation YouTube channel. I'll see you again next time on a different episode of the Simulation Step-Up series. Thanks again and have a great day.